swap any of this, right? X, Y, this is X cross Y give you Z. Y cross Z give you X, right? Z cross X give you Y. So these are right-hand type rectangular coordinate system. And I noticed that some of you still struggling with this basic idea of the coordinate systems, okay? So now where is the wire? So let me use a different color. So the wire is actually on the XY plane. So if I draw it on the XY plane, so on the XY plane, then it'll be somewhere like this, right? Okay, it's on the XY plane. And how much current flowing here? The current flow is I is equal to 4 amps. And it's flowing in the phi direction. So remember the cylindrical coordinate systems? Let's say I pick a point over here. Then this direction is called the R direction, right? And the direction, this direction is the phi. Well, let me put phi hat here. Let me put, so let me use this. Let me erase. Let me use this, what do you call it? I should do this. Oh, no, not that. So this, the unit vector is the R hat in this direction. So let me draw the unit vector here. So you can imagine it coming from here. This is R hat. This unit vector is called phi hat, right? Any questions? So the current is actually, I can write this down. The magnitude is 4 amps. What is the current itself? So what I should write is basically this. Let me erase this. The current is actually, oops. How come I cannot do this? So some glitches still. No. So those, okay, I'm not going to worry about this then. So the current is still 4 amps. So there's some glitches. All right. And the current basically can be written as I is equal to phi hat 4, right? The unit is ampere. Does it make sense? So the current is flowing like this. Okay, so now what is the magnetic field? So this is given. You know that the length here, let me use a different color. The length here, maybe it's a green, the radius, right? This radius over here. So this is basically R hat R, right? What is R? Where? So this is basically R vector equal to R hat R, where R is equal to whatever is given, right? What is the radius? It's given later. So you're asked to solve for R, right? You're asked to solve for what R is. That is weird. Okay. So yeah, you're asked to solve what R is here. All right. So R is basically the radius of the loop. Any questions? So let me erase this part. Okay. So where R is the magnitude of the radius, so we don't actually need this. So R is in the R directions. Any questions? This is what is given. Any question at all? Okay. So now, right now, part A, you're asked to derive the B and H at the center. So where the B and H should be is right here. You're asked to determine the B and H at this location. So let me use a different color, maybe the blue. You're asked to find B and H at this location. What is the B? What is the H at this location? It's a vector. Any questions? So how do we solve that? So now once you set it up, the next thing then is, all right, you are given a source. The source is all the current here that produces the field, right? So what is the relationship between what kind of relationship that if I know the source, can you give me the field? Well, this is from actually magnetostatic, because the current is DC current, is a direct current, right? So it's a magnetostatic, and the law, you either use the Biot-Savart law, which you can solve it directly. Now this is a simpler problem, so you can use Biot-Savart law. Another law that's a little bit more complicated is the curl of, the close integration of H equal to the current I, right? That's another law that you can use, which is the Ampere-Circuital law. All right. Any questions? So because it's electrostatic is easier to solve using the Biot-Savart law. So what I'm going to do, I'm going to use the Biot-Savart law to solve this problem. Okay, so what I'm going to do is I'm going to try to, well, that's fine. So any question up to this point? So I'm going to go to the next page so I can write more here. So the Beard-Savart law that you studied already. So what's the Beard-Savart law? The Beard-Savart law says that the small amount of magnetic field produced. Now I'm interested in the location where it's 0, 0, 0. So now let me draw it. Suppose now I have any arbitrary current, right? Well, this is not a good drawing. I don't want to do that. Just do this simple one. Okay. So just erase this and then get a new one. So suppose I have the, suppose this is my path, right? This is my current. The current flowing through this. So it has directional property. So suppose I'm observing at this location. I want to find out at this location, what is the H and so on. So of course, the B and H over here, the contribution is coming from the entire wire. But I want to know, suppose I'm only interested in what is the contribution from this portion of the wire right here, the small little element, right? So in this case, the whole current is a constant. And then here I have the differential length. I want to know what is contribution coming from this little part. So imagine the current is throughout the wire, but I want to know what is contribution from this little part. Okay, and in order to find that, then I need to know the position from this to my observation point, right? So what's the position? What is the distance and directions? So in this case, the distance and directions are, let me use a different color. So it's this, right? This is my observation vector. Let's call this the observation vector R. Okay. So R consists of the unit vector, whatever I call it, that unit vector R times the magnitude, right? Any questions? So the Beard-Savart law says that d of H is equal to, d of H is equal to I dl, which is a vector, cross with R hat divided by 4 pi R squared. So what is R hat? Again, R hat is equal to the vector R divided by the magnitude of the vector R, right? And R is nothing but the magnitude. Correct? So this is critical for you to the basic vector analysis. You need to know that. So the d of H is basically this vector, of course, it has directions, cross with this vector, right? And divided by the distance, 4 pi R squared. Now, some formula, because this, I can combine this, I can have it this way. This is equal to I d of L cross with this R vector. Now, this is a full vector, but I have to be very careful. Then it is divided by 4 pi R cube, right? Any questions? Okay, so that's what we got. Okay, so these are its differential element give me this differential amount of field. Okay, so now what is the total contribution? So now if I look at what I had earlier, our problem is, what is our problem? Our problem is that we have this, right? We have X, Y, and Z. This is our, let me use a different color. This is our current right here, right? So this is the current flowing there. So so its differential element, here, this is dl, right? And the current through is I, right? The current is I. So the differential current element is IDL. For this particular segment, what is the R? This is the R, right? I'm sorry, I just used the, maybe I should do the vector R itself, all right? So then what I have to do is simply, the Beard-Savart law is now, they're all the same. The R, the only difference now is different angle, the different phi, right? They're all the same, just different phi. correct? The distance is always the same because it is a circle. So the distance is always the same. The only changes is the different phi directions. So in order to do that, I simply have to sum up all of these across this circle. Everybody follow that? And because it's right in the middle, it's easy. There's only one component, right? This cross with this only have the positive z component, right? This phi, which is dl, is what is dl. So let me write it down. What is dl? So this is equal to, let me put yeah, let me just skip the blue. So dl equal to I, what do we have? Phi hat, let's see, dr, right? R d phi, I'm sorry, yeah, r d phi, correct? So this is my d of l, right? It's basically r d phi, and in the phi hat directions, okay? So now the variable I have to integrate now is basically this d phi. Everything is fixed. R is fixed because it's a circle. All right. So now if I put that in the equation, so when I want to sum this up, I basically have to sum up from phi from 0 here all the way to 2 pi. Any questions? So I just sum up every different element, and then so that will give me my total field instead of the differential field. So this in these equations, oops, right? No. This is a differential field right here, right? It's a differential field. So if you sum up all of them, like you sum here, you sum up here, then you have the total field. Right? Everybody follow that? All right. So now, in order to do that, oops. What I can do now is let me put down in the expression. Therefore, my h is given by at the center. So at the center is at what? At 0, 0, 0, right? This is center. X, Y. If I use X, Y, Z is 0 or R. I can do R theta and phi, right? I mean, sorry. The R, and then this R. Then it's 0 phi. You can pick anything because it doesn't matter. It's in the center. It can be 0, and the Z is also equal to 0. So they're all 0, 0 for either you use a cylindrical coordinate or spherical coordinate or rectangular coordinate. So they are the same, right? H0, see, this is the H at the center. So that's equal to, I sum them up, right? First, I sum up over the path, the closed path, I dl cross with r hat divided by 4 pi r square, right? All right, so now if I change this into the phi type dependency, I end up with integration phi from 0 to 2 pi, basically I dl becomes, let me do phi hat cross with r hat, right? And then I have r d phi. And then this whole thing is divided by 4 pi r square, correct? And the integration is over phi, so I can pull everything out that's not function of phi. So I have basically I over 4 pi r square. Phi hat cross with r hat give me z hat, right? In the z direction now. And the rest is simply I integrate from 0 to 2 pi d phi. So you know how to do this integration. You integrate 0 to 2 pi d phi. That's basically 2 pi, right? So the answer then is you have this whole thing is 2 pi. Therefore, that's equal to 2 pi I over 4 pi r square, and then we have z hat. So 2 pi, cancel this out, this become a 2. So what we end up with is, and then I think I have something, I missed something. Oh, there's an r, I forgot there's an r here. There's an r over here. So I have to move the r outside. So r and r outside, let me put the r over here. So put r over here. So r, I have r over here. So r and cancel out one of these. So finally, what do I have? I have equal to equal to z hat. So the field, the total field at the center, this is the field at the center, I over 2r. So that's the first part, right? The magnetic field intensity. How about the magnetic flux intensity at that location? So we know that I told you that this is non-magnetic medium. So the B at 0, this location at the center, is equal to mu 0 H at the center, right? So the B is the same as this, right? So either the B is equal to Z hat mu 0 I over 2R. Now, of course, you can put in whatever number you want that's given. If I know the R, I can solve what the, and if I know the I4, R is this right now is unknown. So if I put the I in here, what do I have? If I put all the numbers that is given to me, what I have is this is equal to Z hat, I is 4 amps, so it's basically 2 over R, right? This the unit is ampere per meter, right? Here we have this is equal to, again, the vector is Z hat, mu 0 is 4 pi times 10 to the minus 7, and then I is times 4 divided by 2R, right? R is unknown. So this you can, so basically you have 8 pi times 10 to the minus 7 and then divided by R. Any questions on this? So this is the first part. Now the key thing is that this is a vector. In some of your paper, I note that carefully. There's a vector, unit vector here. When you do cross product, there's always vector. The result is always a vector, right? So the key here in this problem is actually related to the so-called path integration, except you have to use your calculus 3 stuff, right? Path integrations, and then you have a vector element. You can use it. In this case, you have to use the cylindrical coordinate systems. Any questions?
Oh yeah, sir.
Any question at all?
Is the r hat negative or positive?
Well, oh, you're right. Sorry, it's actually negative.
Oh, okay.
Because going inside, right? This is actually negative, so that's why the cross actually the z give you the z. I just go too far ahead of myself. Yeah, you're right. Thank you for bringing this up. Actually, this is r hat. So this is actually a negative. Well, r hat is this r hat is negative little r hat. Does it make sense? For spherical cylindrical coordinate system. Cylindrical coordinate system. The if I put into xy plane. So the cylindrical coordinate system for here for this point, the r is going out. The little r, there's little r, right, for cylindrical, and here's the phi hat. So our r is actually the opposite of r vector. Thank you for bringing it up. Any question on this? So the phi cross this r hat give you the positive z, right? If this cross with this, you give you negative z. So yes, so this is actually I need to yeah, this is correct. The r hat is this diagram is actually going in, right? So the cylindrical coordinate is in this r. So the r hat is negative r right here. Let me see. I think I have everything's correct, right? Oops. Yeah, everything is fine. Any questions? Any question at all?
Oh shit.
So that's the first part. It's just how about the second part? Now the second part is actually a very challenging question for the second part. So this is at the center of the loop, right? So here, the B, the H, these are at the center of the loop. And some of you cannot even get to the geometry point, just that you mess up the geometry already. So whatever you do afterward is no longer relevant to the problem, right? So first read what is given and then lay it out. Because it's at this point, whenever you have the vector type problem, it is very hard to visualize. So it's best to just lay it out, draw it, sketch it, and then be very careful because all of these are vector, clearly distinguishing vector quantity versus scalar quantity. Now, if I don't put the vector here, it's wrong because I have a cross product right here, right? Cross product, the result will be a vector. So again, if you put cross product without putting vector here, it's not going to work, because cross product only defined for vectors. So it's very important that you have a very, very what do you call it, carefully written up the formulation and as well as the notation. So in this case, notice that you need to distinguish between the unit vector versus the vector itself. So this is unit vector, right? As I mentioned earlier, here, if you look at this formulation, right? So if you look at this carefully, this is unit vector, but I can also, that's why you see formula of this type, the r cubed one versus r squared, because if I use this is not unit vector, this is entire vector. So the entire vector actually divided by the magnitude, right? So that's why you see they are the same thing. This one is you cross with unit vector, this one you cross with the vector itself. Everybody see that? So there's a lot of little, so if you're not careful when you use formula, then you're into problem. Your answer is wrong, right? Any questions? All right, so part B is tricky, because let me explain to you why is it tricky. And that problem was meant to basically ask your understanding of the concept itself. I don't expect you to solve all the detail, and if any one of you can kind of like point out, okay, here's a formulation, but I don't have time to solve it. So let's say, oops. So for part B, let me use another page. So for part B, what is asked for part B? Here's part B, right? I want you to derive. This is, I mentioned this in class, I think a couple of times, that this seemingly simple problem, actually, a lot of people work on it, and finally somebody at NASA solved for in other words, at any point in space. So if you have this circular current flowing like this, at any point in space, doesn't matter here or here or here, and so on, what is the magnetic field associated with it? Magnetic flux density or magnetic field intensity? Our book only tell you what happened on this axis. Why? Because on this axis, you can actually solve it, come up with the equations. Nice looking equations, nice looking function. Anything outside is quite complicated. So in the class, we actually do two special cases. One is, this is the field on this axis. Of course, the exam is the simplest location, where it's right in the middle. And then the other case is when you're very far away. So we have this so-called magnetic dipole. Remember that? When you observe the field very far away, and the equation can be simplified. So that's what we did, okay? Anything else, if I ask you, what is the field over here? This could be a graduate level problem. In other words, actually the solution is quite complicated. Let me explain to you why. The concept itself is not difficult. Here's the challenge. So part B, I ask you to can you derive the analytical expression as a function of R, right, for the self-inductance. So to solve these questions, first you need to know what is a self-inductance. What do we mean by self-inductance? So capacitance is what? Capacitance is how much charge in the system that you can store per unit volt, right? The voltage, correct? Now for inductance, what do you mean by inductance? How much flux that you capture per unit current, right? So you can store the flux by coming up with a magnetic material that can store fluxes. So now self-inductance, what it means is that the circuit itself. So in this case, self-inductance is, in this circuit, is this current produces magnetic flux, right? And the magnetic flux here is being captured by this area. So this is the same circuit. So this current produces a flux, and the same circuit capture some amount of flux. The ratio of that is called the self-inductance. Mutual inductance means this. Suppose I have another circuit somewhere. Maybe let me put a yellow color. Suppose I have another loop over here, maybe a rectangular, whatever surface, right? So then what is the mutual inductance between these two, between this one and this one? So I can solve it two ways. One is I figure out what is the magnetic field produced by this entire current I1 that is captured by this area. So what is captured by this area? Of course, you have to do the dot product, right? Divided by I1, that will give me the mutual inductance between these two circuits. Does it make sense? And the result will be the same. I can calculate, if I know the current over here, I can calculate how much flux being captured by this particular circuit here. And the ratio of the flux captured here by the amount of current over here is called the mutual inductance. Any questions? So self-inductance, I can have self-inductance of this guy by itself. So I can have suppose I have a current flowing. Let me use a different color here. Okay, that's good. If suppose I have a current flowing like this, let's call this current I2, right? And this current I2 produces magnetic field. And the magnetic field that's a magnetic flux that captured by this amount of area, the ratio of that magnetic flux captured by this area divided by this current I2 is called the self-inductance for this particular circuit, this particular setup. Okay? The self-inductance for this guy is this current produced magnetic flux captured by this area here. The ratio of that is the self-inductance of this part. Now, between the two of them, what is a mutual inductance? This current produced magnetic flux captured by this area, the ratio of the one that captured by this area due to this particular current divided by this current is called the mutual inductance. Any question about that? All right. So this part B, so let me erase this. I don't need this anymore. So part B, basically, do you know what is the meaning of this self-inductance? And once you have the self-inductance, then you realize, okay, actually involved to solve for the B. So let me write it, right? So part B, oops, no, I don't want this color. So part B, we have the definition of self-inductance. Let's call this L11, right? By itself, right? Equal to the, in this case, I only have one loops. So I just use the flux generated by the current one also captured by the circuit one. So I do phi1 divided by, or phi11 divided by I1, right? So this is captured by the circuits one and then due to current one. So then this is equal to, you sum up the surface area, and this B, of course, this B is functional position, right? It's function of the R, function of phi. Now the Z is 0 because it's on that plane, right? The loop is on the plane. This vector, you dot with ds. And usually we'll pick the area so that the result is positive, right? In other words, once you give a sense how the current will flow, then this will tell you either positive or negative inductances, right? In other words, the current, your presumed current flow. So this divided by I1. Any questions? So what I have to solve now is that if you look at the diagram, I have a loop that looks like this. Here the current is I1, right? And then, so if I use this as my sense of the edge, so let me, this doesn't look that good. So let me rewrite this one. So the current is here is I1, right? I1 produces magnetic field. So let's call this B1, right? So produce B1. So where is the B1? B1 actually going, let me use a different color for the magnetic field. The magnetic field, maybe let me use a blue color. So you have, of course, magnetic field always, right? So you have this magnetic field. Actually, it's doing this, right? Actually going around, right? Magnetic field, correct? All over. So basically you have this, of course, this going all the way and it's coming back, right? It's a loop. Here's the magnetic field. Any questions? And we know, so here's the plane. So let me draw the plane. The plane, XY plane is maybe this is the center. So you have here's my Y, here's my X, here's my Z, right? Any questions? So here are the flux. So the flux will be captured by this area over here, right? This is the area. So now you can see that in order to sum this, I need to find out the B at every locations. So maybe for, let me use a different color now. For this location, for example, I want, what's the phi? So here's the R. Oops. Let me. So here's the R, the vector R, right? And here's the phi. So, all right, here's the R, the distance, and the phi. So it's function the R. So maybe just, if I want only look at the distance, then I need to have R phi. And then because on the plane, I don't have to worry about the Z, right? Everybody follow that? So I have to solve for the B at every point. So the concept is no difficult. I'll show you the concepts. So any question about this idea? So you have to sum up all the flux that's captured by this and then divided by I1. That will be your self-inductance. So if you set this up already, you already get some partial credit because at least you understand what it is. Okay. So what is D of S? D of S simply the Z, right? In other words, now you're going in these directions. So the surface normal is going in that direction. So D of S, I can draw them. Maybe I should use a different color. The green. So here's D of S, right? Any questions? So, okay. So the question now is, the challenge is then, how do we solve for this? So in order to solve for this, again, we apply the Biot-Savart law. All right. So now the Biot-Savart law, what does it look like? So let me see. So now if I will turn it around, I'll just draw the XY plane to make it easier for you to visualize. So I now, maybe I just do this. This is my X. This is my Y axis, right? And then my Z, of course, is coming out, right? My Z axis is coming out. So let me not draw the Z axis, right? So this XY plane. So this might call my XY plane. Okay. So now I have my current. The current is going around like this, right? This is my current. Okay. So now let's suppose I want to find what is the field at this location. Let's pick a field at this location, right? I want to find out what's the field at this location due to some element, differential element here, right? So suppose this one is the differential element here. So this will be my I dl over here. And this is our R, right? Correct? So I know this position over here. This is the position of my current. Oh, boy, that's kind of messy. Let me see if I can redo this. Let me put an extreme case. Suppose I have I want to observe over here. This is what I want to observe. Okay. And then my current that I'm interested in maybe over here, just right near the arrow here, right? I want this my IDL. So from Biot-Savart law, it tells me that I need to find out what is this R, right? Okay. So what is the location of this? Well, the location of this current is basically this is R, right? This basically R vector here. And what is this? So this is the location of the, let's call this point, this vector, let's call this vector R prime, right? Any questions? Oh, this I should do the let's call this R0. So this my observation point is R, okay? No, sorry. I know it's kind of confusing. Let's call this R, and let's call this one the particular point that I want to observe R0. Okay? So the Biot-Savart law, what you need is this one and this one, right? This cross with this, divided by 4 pi magnitude of this R square. Okay? Now that's why this is messy now, because, so now let me show you how do we, oops, I need to move this. I don't want to turn it around. I can make it larger actually. All right, so let me move it up. Okay. So now the relation that I have is basically the Biot-Savart law. So the Biot-Savart law again, oops, a different color. that we had earlier says this, right? D of H, the differential element for the magnetic field intensity of any location R, phi at z equal to 0, right? So this is equal to, so this is on the xy plane that I show over here on the xy plane, right? So where z, on every point here, you only have R value and phi value, right? So at this point, you have this is the R, this is the phi, right? So any point in space I can pick. So for example, I pick a point. Let me use a red, a red color here. I pick a point over here. So in this case, this value here is the R. This is the phi for this particular point. Does it make sense? So at every point inside, I can, as a function of R and phi, any in the position R and phi, but at z equal to 0. All right. So now these are the differential element at any point. So how do I solve it? What is the differential element? Well, the differential element actually, according to the Biot-Savart law, what I have to do is this is equal to I dl cross with, now this is what messy, R vector, I call this, yeah, R prime, right? The R prime right here, this one, I call this one R prime, the location of this, right? This vector minus this vector, right? So this vector is nothing but this vector minus this vector, right? From your vector calculus. So this is equal to R prime minus R, right? And then you have to divide by 4 pi, the magnitude of R prime minus R. And then you have to, because I use the full, I have to, this is the third power, right? Any questions? So this is what messy, this is what messed thing up. Or I can rewrite it, this is equal to I dl cross with, now I have the unit vector, which is R prime minus R divided by magnitude of R prime minus R. So this becomes the unit vector in these directions, the unit vector in these directions, right? So this term is nothing but the unit vector in these directions. Then the denominator is then divided by 4 pi, which we had earlier, the distance between R prime and R square. So what's messy? What is complicated? To solve this, now you're dealing with something called elliptic integral, because this thing is it's not difficult, just a messy function, as I mentioned before, right? Magnitude, this is what causing all the problem. So to integrate this then becomes a challenge. So the integration is becoming a very messy, because you have to integrate the whole thing over R and phi, right? You have to integrate the whole surface. So what you have to do now, you have to integrate the whole thing. Next thing is the phi, the h at any locations. So thus, oops. So the h at any locations at any location R, phi, and z equal to 0, you have to sum up the contribution. So in other words, the field at this location is contributed by this guy here, by every single one of them. You see that? So you have to sum up for all, for field in this location, you have to sum up for the contribution for the entire thing. This point the same way. For part A, we only solve for the field in the center, because in the center, everybody contribute in an equal way. The vector is very simple. Now the vector is very complicated, right? Not complicated, messy. So to solve that, then it's actually this is equal to, I have to integrate over the area. So I have integration, the R, of course, this R can go from the smallest 0 all the way to twice the distance, right? All the way from the closest point. So for example, if I pick a point over here, extreme case, I have to sum from the closest distance all the way to the furthest distance. So the R actually goes from, so let me, so this is I have to sum from very close distance R to quite far away, maybe 2R, right? Maximum is 2R. And I have to sum the phi, right? From 0 to 2 pi. And now I have this whole thing. I have this I dl cross with, maybe let me use this r prime minus r divided by 4 pi magnitude of r prime minus r magnitude to the cube. And then the ds, what is d of s? D of s basically the r d phi dr. So that's the area, differential area. So I have to solve this. Now this seemingly looks simple, but when you try to solve these, there's a complicated function of phi and so on. So it's rather difficult to solve. But we know that. What we know something interesting. We know that um, the field in the middle is the strongest. As you go out, it gets weaker and weaker and weaker. Toward the end, it's relatively weak, right? So actually, it's not the same. Now, if the circle is not that big, then you can approximate it's about the same. So for this part B, if you say, well, assume the field is the same here, well, I'm okay with that. Or there's some value less than that, I'm okay with that, right? So I just want to get your understanding about um, the idea of mutual inductances. I mean, no, the self-inductance, right? Any questions? If you derive this, I give you a perfect score, even though you don't solve it, because to solve this, it take a while to solve this. Any question for the second part? The idea itself, right? Any questions? So I thought that I thought I can give you a lot of, some of you may recognize, oh, this is what we talk about in class where the solving is quite complicated because of this messy distances function. Remember we talk about, then you can do the far field approximations, or so the only one that's straightforward is the one right on the z-axis or in the center or very far away. Then you can make approximation to these things. That's the whole idea, right? This is just make it messy and involves something called elliptic integral. I don't know if you guys learned that in your calculus 1 or calculus 2, elliptic integral. So some special type of integration. So the formulation doesn't change, just now how to solve this is kind of tricky. So if you use the approximate using the field in the middle, that's okay, but that's overestimate, because the field here is the strongest. As you go further out, it gets weaker. So technically speaking, the total flux will be less than the flux in the middle, the flux density in the middle multiplied with the area. Does it make sense? Any questions? So that's the second part. Any questions? Now for the third part, I think some of you mentioned this earlier. What is being asked for the third part? Well, now you're supposed to determine the radius of the loop R. If I know the self-inductance, let's see. Oops. Yeah, you're asked to determine the radius of the loop R and the associated the corresponding self-inductance if I give you the field intensity 30 amp per meter at the center of the loop. So to answer this question, you need to know two things. Number one is, well, basically once you derive the first part, you just plug in the value of R, you get, you can solve it, right? The second thing is that, do you know anything about the plugging it in? So the formula actually is the same. You just now substitute. Yeah, if you approximate the field as the magnetic flux density the same throughout, then you just plug in that formula that you have. Okay. Does that answer your question? So the first part, for example, let's do the first part. What is the loop size? Well, what is our equation earlier? We have this, right? The field intensity is given 30 amps per meter. So 30 amps per meter at the center of the loop. So now what we solved earlier, right here, at the center of the loop, this is the equation, right? We know the currents. So we now know this is what? How many amps per meter? 30, right? We have 30 amps per meter. So what we have to do is simply, this is equal to 30 amps per meter. So 30 amps. So what is R? It's a Z hat 30 times 30, right? So what is 2 divided by R? R is 1 over 15, right? Any questions? For the second part, if you approximate it as a B dot ds as some kind of simple value, again, you have a function of R, and then you can solve that. You just plug it in, the substitution. So that's meant to be, again, a giveaway type. That's why the point is relatively smaller than the other two. All right, so let me kind of pause here. Any questions? Let me turn on my video so you can see me. I'm still here. It's not recorded. It's live. Any questions?
What was the self-inductance equation again? Like
Self-inductance.
for C.
Okay. Well, the same thing, right? The self-inductance is right here. Let me see. Oh, I thought I have it earlier. Let's see. Oh, no. Let me see. Oops, no. Let me just. Oh, not here. So maybe the third part. I probably moved the third part. Right? Oh. So I see what happened. I think, oops, I don't want to move things around. Sometimes when the software is too smart, there's no. Here it is. So here's the definition of the self-inductance, right? Right here. So what I'm explaining to you all on the second problem is that this thing is complicated. But if for this particular test, if you assume that this is the same throughout for you're assuming that, okay, assuming that this is not too big, so I can approximate the flux in here is approximately the same as the one in the center. That's fine. Usually smaller than that, so you can have some kind of ratio or some kind of factors, but that's not critical. I'm just looking for, do you know this? All right, and then if you assume that this is the middle, the same value for throughout constant value, then it's just simply this times the area, right? So the self-inductance is simply your B times the area divided by I1. Does that answer your questions?
Yes, sir. Thank you.
Yeah. Yes? Who else have questions? Now, the exact solution is rather complicated, but as an engineer, I did also during tests, you just, well, there's no way you can solve this in that time, right? So I'm not looking for that. I'm just looking for, do you know this idea? And then give me some kind of estimations. Right, since you have it already, and most people don't even think about it, right? Actually, it is not the same inside throughout. But it's okay if you give me you approximate the center, then that's fine. Then you get a lot of credit. Any questions? So what I'm after is this idea. Do you know what we mean by self-inductance and what we mean by capacitance? Now, capacitance, there's no self-capacitance or because there's no induction involved, right? It's everything's local. Whereas magnetic field, you can have basically the circuit is kind of, you can have 2 or 3 circuits by itself. It creates a flux. It can also capture its own flux. If it captures its own flux divided by the amount of current that produces that flux, that will be your self-inductance. Mutual inductance means that someone else has produced a flux and how much you capture. So the ratio of that to your current, that will be a mutual inductance.
Professor, can you explain the X and XY plane again? Like why did you label R naught and R initials and all that?
Which one? Which diagram over here?
That one.
Okay.
Yeah.
All right. So for this one, what happened? For this one, I try to explain that this magnetic flux density or magnetic field, right? One of those. This B or H on the plane, they actually function on position. They're not constant. Okay. Does it make sense? At this point, we know how to solve the center one, which is the simplest one, easy, right? But as you go out, then it is complicated because the Biot-Savart law tells me that the contribution of this guy to this particular point is this vector right here. But for this guy to contribute to this point is a different vector. Does it make sense? So for a particular point in this space, what is the total magnetic field or total magnetic flux? I have to sum up the contribution for all of them. And that's what this expression, that's what this expression say. This is what this says, right? So it's actually, I do not, now you finally convert into the expression in terms of phi and r. It's quite complicated. Then it becomes very messy. So to solve this integration, you have to use something called elliptic integral. If you, again, I mentioned earlier, last time, if you're interested in how the NASA folks actually come up with a paper solve for the whole, you got a loop, can you find out the field at any position in space? There is a way to solve that. There's a formulation. If you're interested, I can give it to you. You can take a look at it. Does that answer your questions?
Yes, sir.
Okay, any other question for problem number 2? The biggest issue I saw when I grade your exam, or when I do the looking back at what you did, a lot of you have difficulty with the coordinate system. This curl product seems to throw a lot of people off. The curl things, the kind of curl, let me see. Yeah, usually the one that throw a lot of people off are this kind of stuff. This curl, what directions, and then some of you mentioned earlier about, is it, I'm glad that you point out this has to be minus r directions, and the curl, what you end up with the vector. That seems to be some of you have difficulty with those, and not one or two, but quite several of you have difficulty with those. So you need to go back and kind of review your calculus 3. At least make sure you get it clear. The coordinate systems, the curl, the divergence, and the vector operation, dot product. So make sure you have those, because this is relatively simple, but it's hard to visualize. That's why I encourage you to sketch it out. Once you sketch it, then you can see it. Any questions? So now let's go to the next problem. Yeah, originally I was thinking maybe one of you can present, but then you don't have this white. Well, you can do it whiteboard, but they don't have the easy way to write it. So maybe let me go ahead and just do the third problem. So this is the second problem. Okay, now let me move. Let's see. Oops. Here's the third problem, right? Now the third problem has two circuits. Now I have two pieces of wire, two separate pieces of wire. So you can think of there are two circuits involved, right? Okay, maybe let me turn off my video so that it doesn't take up the bandwidth to get to you. All right, so in this case, you can see that both carry current. So when we are both carrying current, what happened? You expect there be forces on both of these conductor, right? Okay, there be forces between them. So what is given? This one is infinitely long wire, carry a 15 amps. They're two different current. I don't know, some of you forgot and you use the same current. That is a wrong problem. The second one has different current. The current flow this way. So the second one is a closed circuit. The first one is an open, well, not open circuit, but a straight line. The other one is a loop, right? Now, if I give you a loop, to solve for the field from the loop is quite complicated, right? So now, so we have a straight conductor. I tell you what the current is. Another conductor, I tell you what the current is. And I did not specify, or generally this kind of problem do not specify the coordinate system, right? But you know the spacing here. The second from the current is spacing with D. The width of the loop is W. The height of the loop is H. Okay, so that's given. You know what D is, 0.1 meter. You know what W is 0.25 meter. H is 0.5 meter, right? So let me kind of lower it up a little bit. Okay, so let me put it down here. So this is D is equal to 0.1 meter. W is 0.25 meter. This is 0.5 meter. So I1 is 15 amps. I2 is what? 30 amps, right? So that's what's given. So what is being asked? What is being asked is, okay, now of course some of you just solve it using rectangular coordinate system. Can it be done? Yeah, of course, because this problem is very straightforward. You don't need to use any, either way, either rectangular or cylindrical should work. But cylindrical is more natural. But I do not take points off if you do rectangular. If the answer is okay, that's fine. So what I asked, the first part is that, okay, since you have two current in two circuits, so what happened is that this wire will experience forces because this wire over here produces magnetic field. And because you have current flow here interacting with the magnetic field, you'll produce forces. But what I'm asking you is, what is the forces? What are the forces or the net force acting on the entire circuit here, right? as a whole. So as a whole, of course, you have force acting on this piece, you have force acting on this piece, you have force acting on this piece, and so on. Now forces are vector, so the net force will be the sum of all those vector, right? Sum of the forces acting on this piece plus this piece and this piece. Any questions? So that's to answer the first part of the question, I need to solve for forces acting on this one, forces acting on this one, forces acting on this one, and forces acting on this one, and then I simply sum the vector. So I have to do vector sum of the forces together. That will be my net force on this particular circuit, right? This particular loop. Second thing is, what is the mutual inductance? So that is where I want to know whether or not you understand what do we mean by mutual inductance, L12, meaning that this is this captured by the second, the flux captured by the second circuit, the flux is produced by the current number one, right? This current produces flux, and how much is being captured by this circuit number two, right? Which is kind of giveaway already, because here's the area, and then you know what is the field produced by this current, and you simply sum up the dot product of the field with the dot product of the area divided by current number one. That will be your mutual inductance. That's it. So before you solve, make sure you know what you need to do. Any question up to this point? All right, so now let's go try to solve that. So I think this is all right. So if I draw it now, what do I have? I have a current here, and I have another loop, right? Of course, these are all closed circuit now. I have current going this way. So this is 15 amps. This is 30 amps. And here the spacing is between here is 0.1. Let me not write down anything after that. This is 0.25. All in meters. So be very careful with unit. This is 0.5. All right. So what do we know? Well, first I need to know, in order to calculate the mutual inductances, I need to find out the field first, or the magnetic flux, and then I need to find out the area. So the easiest one is that this area is ready. I have the area right here, right? Ready made. So what I have to do is simply find what is the field due to this current here. Any questions? So I know how to find. I can use the Ampere circuit law, right? Which is what? And you've done this many times already in the homework as well. So what we have here is the closed path. Oops, maybe I should use different color. So we know that the closed path of integration, the right hand, h1 vector. Of course, this h1 is function of distance from the y itself, right? Basically the r. So now, before I solve that, let's define the coordinate system that will work for us. So let me go ahead and erase this. So what do we want to, how do we want to set the coordinate system so that it's easy to solve? So let me use a different color, the green color to the, so I can, because this is symmetrical, usually when you have a long line, you want it to align, right? You want to align this to a particular axis. So in this case, if we pick, I already told you to use cylindrical coordinate. So naturally, I want to align this with the z-axis, right? So going out will be my r directions, okay? So I can have the following. So this will be my r directions here. This will be my z directions. Any questions? So this then will be, I can pick this plane to be when phi equal to 0. So in other words, now if I draw this, so if I draw this, what do we have? So this is the idea. I have z. So let me just draw x, y, z. X and y. So I can think of this plane. I can think of that I can pick any plane as a matter of fact. I can use x or z. I can think of it this way. I can, let me use a different color for my circuit, right? So for my circuit, maybe here is my wire going through here. Okay, this is the 15 amps. And then I assume that this loop is actually over here. Can I do that? Right? So again, this is going here this way. So this is equivalent to phi equal to 0. I can do it that way. Does it make sense? So I can pick a different location. I can pick maybe a different color. I can do whatever I can put it on the Y actually. I can define it that way. So let me use a different color. I can say, oh, actually, this doesn't change, but my loop is actually over here. So what's the difference? The difference here is here the phi is 90 degree, right? Pi over 2. Correct? R is the same, right? R is the distance from here. So this is the R directions. Does everybody follow that? So I can pick. So if you decide to use X, Y, X and Z, that's fine. Or Y and Z, that's fine. Or I can just use R and Z. And here in this case, I can assume the phi is equal to 0. Okay. So I can use this. In other words, now I'm on the XZ plane, or I can be the YZ plane. It doesn't matter. Any questions in terms of how you pick your coordinate? So I suggest that you put this going out as a distance away because this one has cylindrical symmetry, right? So this is a distance away from the wire here, and we can pick one phi, whatever phi is. So the simplest phi is phi equal to 0, right? This is on the plane for phi equal to 0. Everybody follow that? Is that clear? So some of you do use the rectangular coordinate this way or this way. Now, if the logic and the answer is correct, usually there's no problem. I do not that point off, even though if you don't use the cylindrical coordinate. Any questions? So suppose I use the cylindrical coordinate system like this, right? So going out is how far away from the center, from the axis. So that's my R. So based on, then I can use the Ampere circular law. I know that. So I'm going to use the cylindrical coordinate, right? So here I find, in other words, now for this, let me write it down first. I've picked a path C. So this H1, what this is one function of R, phi, and Z, right? Oh no, actually it's not function of Z because it's an infinitely long wire, so it's not a function of Z. It's function of R and phi only. And we studied some time ago. And then this, remember, vector, we have to dot with dl. This is equal to the surface and the current density 1 dot with ds, right? So what does this expression mean? What does this tell us? What does this tell us? This is what you need to understand. So what it tells us the following, if you still remember. What we have here is basically, I'm looking at the current due to the first one, right? So I have a current that is flowing called I1. So I1, what is I1? So I can think of this, I can have, here's a closed loop. So let's call this closed loop C, right? This is a closed loop, we go in these directions. So the area covered by this loop is this area, right? So the area is this S. Okay, everybody follow that? So the current will produce a field that is like this. This is the law, right? And so same distance away, the field is basically constant throughout, right? We know that. Okay. So if I fix my R, so I fix my R. Let me use this. So I fix this R. I fix this, the magnitude R. If I fix this, then the field will be the same, right? And what is DL? So the H, in other words, it says that the H, the right-hand rule will tell me that if my current flowing these directions, my field will be going in that directions, right? It's going to be the phi type. So our field here will be H1 So the H1 function of R phi actually is equal to, it's not, because same distance away is not function of even phi, it's just function of R, which is equal to some constant value, right? Which is function of R and phi hat. So it's a vector because it's the direction is, so if I plot it, the H will all be in that directions, right? And d phi, dl, what is dl? dl is simply the R d phi, right? And then the direction is phi hat. The differential element, the length is R d phi and phi hat. Phi hat dot with the phi hat, right? This dot with this, what do we get? We get a 1. So this integral give me a scalar after I sum them up, right? So by doing that, what do we have? This is equal to, oops. So this is equal to, so this, let me rewrite it, closed contour H1, which is now we know is function of R only dot with dl. This is equal to, this part is equal to H1 function of R only and integrate over 0 to 2 pi R d phi, right? And the right hand side, what's the right hand side? Well, the right hand side, this whole area, how much current flow? So this is sum of all the current flowing through this area, right? And this current is perpendicular to the area. So the total current, I tell you already what the total current is, 15 amps, right? So this is basically 15 amps equal to 15, right? J.es will be giving me the total current flowing through that. So the J is in that directions and dot with ds. So basically the total current. Any questions? So that's equal to 15. Therefore, I know what so this is nothing but 2 pi r, right? So now what I have is that my H1, the magnetic field intensity due to the first, oh, yeah, this is the scalar now. So my H1, which is function of R, equal to 15 divided by 2 pi r phi hat. Any questions? So here's, of course, the scalar. This is basically what it says that therefore from here, the H1, which function of R only is equal to 15 over by 2 pi r, right? R is just the distance away from the axis itself, the y itself. But now if I put into a vector, I need to tell you what's the direction where this the magnetic field pointing to. Any question, anyone? So good. So now we finished the first part. So I know what the H is. So now I want to do is what are the forces, right? Maybe I just use this next page. What are the forces? So this, oops, this current I1 produce field, right? The field is basically, if I think of the page going in on the page, so this field have to be, it's all going in here, going out, right? It's a loop. So I just get a cross-section cut. Everybody see that? It's a loop. So assuming that the page, this is the Z, here's the R, right? Or you can pick one, or it can be X, or it can be Y, right? Or it can be Y, whichever one, doesn't matter, right? So here's the I, and here's the our axis. And the magnetic field here, basically, of course, the further out you go, is the weaker it gets, right? So here, the closest to the Y is stronger, this is weaker, right? So it's kind of going in, it's going in here, going out from here, right? Any questions? So it's going in, so this is stronger, weaker. As you go further out, it's because it's 1 over R, right? The H, due to the first wire, is the magnitude. Of course, the direction is, so we say the phi is going into, the phi is going into this page over here, and here is going out, right? So now, let me write down the H. So H, I'm just writing the magnitude. The H due to the 1 is function of R, which is equal to the 15 amps. Is that 15? Yeah, 15 amps divided by 2 pi, whatever R is. So the larger the R, the weaker the field. So the further away you are from the wire, the further away you are, the weaker the field. Okay? Any questions? All right, so now, if I put a circuit, let me pull this down a little bit. If I put something over here, right, I put a loop, maybe use a blue color. So now I have a loop here. Let me put the bottom edge line up with this particular axis to make it easier, right? So what's the current flowing through here? I have another current here, 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 right? So this produces, the first current produces the field. Now I put a current to here. Guess what? You have the Biot, no, not the Biot, but rather the Lorentz force, right? The current flowing through here will interact with the field and will result in forces acting on all of these branch. Now, of course, this line also suffer forces due to the field produced by this guy. How much force? Well, the field produced by this loop cross product with the current flowing through it. Everybody follow that? Is that clear? So now, I want to know what are the forces. So now, what is the so-called magnetic forces that we've learned before, right? The Lorentz force. So now I also have to do it this way. For each, I know the current flow here, right? So how does it affect on each element? So suppose I pick a small element. Let me use a different color, maybe red. So suppose I pick a small element here. I want to know what force acting on this small element. So this small element is what we call I dl, right? So I know the magnetic field here on the element. So how much force acting on it? So over here, what is the field? The field is, so let me use a different color here. So the field, let me use green. So here's the current. The field is actually going in, right? Can you see that? The field is going in. Here's a H at this location. It's going in. And the current is going this way. The current is going this way. The field is going in, right, at this location. So this wire will have some forces acting on it. How much force? Well, this is what we had discussed before, right? The differential magnetic force is, oh, by the way, no, let's do this. dF magnetic force, the differential force associated with this particular location is equal to, maybe I should string it down before yeah. So let me string it down so I can have more space to write on. So here, the force, oops. The force on this element is what? The force on this element is dF magnetic force. Again, it's forces are vectors, right? Forces are vectors. So dFm is equal to I, in this case, the second current, right? I2 dl cross with whatever magnetic field produced by the first current. Okay, any questions? So I just have to sum up each segment because each segment is by itself. This one, the field actually is constant, right? Because it's the same for this one. The magnetic field is the same, right? Because it's the same distance away from the axis. This one, again, the magnetic field is all the same, except the magnetic field here is stronger than magnetic field over here. How about this one? Well, the magnetic field changes across, but these two are exactly the same, except the currents in the opposite directions. Now, because the currents in the opposite direction, what do you expect? The force will be opposite direction. So the two of them will cancel out, but we can see what the force is. So what's the force? The force is that basically this current cross with B. So this direction cross with B, what do we get? This cross with something going inside. Where's the force? The force actually for that axis, let me use what color would be good? I used red already, blue already. green. So maybe I use yellow. All right. So for this particular piece of wire, the force is going in that directions. Right. Let's call this F1. Right. Oops. So let's call this F1. For the bottom part, where's the force going? The current flow in these directions. The field is going inside. So what this cross with this, what do you get? Well, the force in this case is going this way, right? So this is the opposite. This force going that way on that piece of wire. How about this one? This one, the force going this way. Any question about that? So before we solve, we figure out where is the position of the force. So now here, now we assume that our loop is rigid, so that this will not compress it. So this cancel out the force, right? The top and the bottom force will be canceled out. Now this one, are they canceling out? They're not. Even though the current is the same, but the magnetic field is stronger here and weaker over here, right? So then you have a net force kind of going in that direction. You push the whole loop away from the wire. So then we just have to grind through piece by piece. What is the first force? So this here's, I call it the F1. This is then F2, F3, F4, right? F4 is the 2 and 4 are the top and the bottom. So 2 and 4 are top and bottom. I don't have to worry about it at all because this, as far as the net force is concerned, they cancel out. These are the one that I have to worry about because here is stronger than here because the field is stronger here and weaker here, right? So I have to solve what is the total force for this particular piece of wire. Well, I know the force for differential elements. So what I have to do is simply sum up for the entire length. So that's what we have to do. So F1, for the first part, of course, is a vector. I put F1. By the way, I have to put all the vector here. I have to put vector here, vector here, vector here. And I'm very picky of this because it's very important to be very clear, right? F1 is equal to, you sum up, right? I sum up from here to, from this point to this point. What is the, this is where the height is 0, right? And here I can set it as a reference. So this 0 all the way to 0.5. So I can do this. This F1, oops, let me erase this. Basically, it's equal to sum up from 0 to 0.5 meter, right? And what I have here is I have, this is my, dl is d of l is minus z dz, right? So here, let me write down. So d of l over here
shit. Here we go again.
is equal to minus z hat, because z hat is going in the opposite direction of dz, right? So again, a lot of people have difficulty with this part. So what we have now is basically I2, second current, minus z hat cross with, what is B1? B1 is in direction of phi, right? And then I have multiplication, I have mu 0 I1 divided by 2 pi r. And then, of course, I evaluate r. In this case, at this location, what is r? R is 0.1, right? So I actually have to change this to 0.1. And then dz. Any questions? Any question at all? So I just sum up all the little forces on every element. I just sum up the force here, 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 every element. Okay. It turns out that my magnetic field or magnetic flux over here, they're all the same value because it's only fixed distance from there, right? So that's the value right here. Mu 0 I1 is known. Mu 0 is known. This is known. So this is a constant. Okay. So this minus z hat cross with phi give me this direction, right? Which is r hat, right? And I2, so I basically, that's what I have. So this thing, let me write down. This is nothing but the r hat directions. It can be a z x hat direction. It depends on how the coordinate system you use. So what do we have now? What we have is basically, this is equal to, this is known, right? So if I don't put in the number, I have mu 0 I1 I2 and then divided by 2 pi times 0.1, so it's 0.2 pi, right? Times the height, which is 0.5. Any questions? So that's the first force. As I mentioned before, I don't need to calculate this one because the F4 and F2, because they cancel out. I only have to figure out F3 because they are the opposite direction, right? So they will cancel out each other, except F3 is weaker. So let's see what F3. Oops. I want to move the whole thing at the same time. Any question after this one? I've been talking to my, mostly the whole evening. That's not good. So F3 is equal to the same thing, except, again, we sum up from 0 to 0.5. Again, I2, right? Except the current is now in Z hat direction, right? Cross with phi hat. And then I have mu 0, I1, the same thing. 2 pi. Now the R is 0.35, right? dz, right? Because here is 0.1. From here to here, of course, this is not drawing to scale, it's 0.25. So over here is from 0. So the position, the field on this location is, as far as the field is concerned, it is a 0.1 plus 0.25 away from the current here. So I know exactly, they're all the same on this wire. Okay. Any questions? So now, so if you work this out, the rest is just, so that's the only difference right here. This is the only difference compared to the previous one, right? The rest are the same actually. So then you have the third one is the only difference, also this one. So Z hat cross with phi, what do we have? It's minus R, right? Minus R hat. Right? Because it's now it's going inward. So this minus R hat directions. It's going inward. So let me write everything down. So let me go ahead and erase this one. Let me put down. Oh, I forgot to put the vector here. Sorry. So the vector here should be R hat, right, for this one, because this, right, this goes to here. So now I have minus R hat, and then I have mu 0, I1, I2 times 0.5 divided by, now instead of 0.2 pi, I have 0.7 pi. Right? That's the only difference between this, the on the left hand side and on the right hand side. The pieces, right? So the difference between the forces on this side and the forces on this side, the difference basically, one is going that direction, the other is going this direction. This one is stronger than that because the denominator, this one is larger, 0.7 pi, right? And here's so after you sum the force, you cancel out. So basically the total, the net force is this force minus this force. And that's it. Any questions? So the answer then will be, you can get the numbers. And I don't have the net force contribution from these two guys over here is 0 because they cancel out, because they get exactly the same thing, right? The field are all the same across the wire between these two. The only thing is that the current is in the opposite direction. Here, the current is also opposite direction. Therefore, the force will be opposite direction. But for this one, the field is stronger. It's closer to this, the source of the field here. This one, the field is weaker. Therefore, it'll be pushed away. If I reverse the wire current, then what happened? It'll be pulled toward the wire. Everybody follow that? Any questions? Let me pause a little bit here. Any question at all? All good? Okay, so let's do the second part. What's the second part? The second part, let me go back here. The second part is, the mutual inductance. So what is the mutual inductance? Determine the mutual inductance L12. So well, we know. So actually, from first part, we know what's the current, the magnetic flux generated by this current, right? The flux density. Can y'all see me still or no? Everybody's okay? Okay. So now the flux density, we know the flux density produced by this guy. So what I have to do is simply the mutual inductance is how much flux density generated by this I1 captured by this second circuit. Well, basically sum up all the flux density here across this area, right? And divided by the current over here. That will be your mutual inductance. Any questions? The general idea. Okay, so let me solve that. So the mutual inductance, part B. So again, L12. I think if you read the book, well, the book gives you all kinds of symbol. So you have this, typically you have lambda 1, 2 divided by I1, right? The key thing is that, what does it mean? It means that the flux, total flux capture may produce by the first current captured by the second area, right? Now this, of course, if I have multiple turns. Multiple turns means I have more and more surface. One turn give me one surface, two turns give me two surface, right? So generally this is equal to whatever number of turns and times this. The convention is that the capital phi denotes the result for single turn. So this is n, whatever number of turn of phi 1, 2, right? Divided by I1. Now in this particular problem, how many turns do we have? We only have one turn. So I don't even have to worry about this n. So how do we solve? So in order to do that, this is given. We need to just simply find out what is this, right? So phi 1, 2 is basically equal to the surface 2 capture B1. Of course, the B1 is function of distance, right? Dot with ds. ds2, right, basically. So usually we pick, I can, suppose I assume that my circuit is doing this. Let me define over here the path. To make it simpler, let me define the path this way, right? So if I use this convention, then my ds is going in the inside the direction, right? The ds is going in, okay? This is my ds2, right? So my s2 is facing inward. Does it make sense? Facing inside the page. It's facing inside the page. Okay, so I define this path. So what I'm interested in this s2. So basically, ds2 in this case can be, I may equal to phi hat, and then this r d phi dr, right? So I have to, r is from this point to this point, this r, right? Phi is, I'm sorry, not d phi, but dz. Sorry, it should be dr dz. So let me erase it, let me redo it, because now I'm integrating this. Oops, something's not working. That is weird. I refuse to clean up. All right, let me cross it out then. We'll worry about this later. So ds2, the direction is phi, and direction is phi hat, and then if we call this r, this is z, so we have dr dz, right? Any questions? Any questions? All right, so now b is function of r only, so I have phi 1, 2 equal to, I have to integrate, my z is between from 0 to 0 0.5, right? So 0 to 0 0.5. My r is from 0.1 here to 0.35. So now I have my B. My B is actually it's a phi hat mu 0 I1 is that's the first one that generated, and it's 2 pi r dot with my ds is also phi hat. Then I integrate over dr dz. Any questions? Phi hat dot with phi hat is equal to 1. So that is very straightforward. Then we end up with 0 to 0.5, 0.1 to 0.35, and phi hat, no, phi hat is gone because it's the dot product, right? So what do I have now? I can erase that for some reason. So, and then what we have is basically mu 0, which is known, I1, which is known, divided by 2 pi r dr dz. Well, I can go ahead and integrate the dz first, right? So dz is simply, nothing is function of z here. So it's simply multiplied with 0.5. So I end up with 0. Oh, let me rearrange it. All right, so this equal to, oops, let's see. This is always messing up. So this software still have some glitches, but it's okay. It's better. So here we have all of these are constant. Mu 0, I1 is constant. What else is constant? H after that I multiply with 0.5, right? I integrate the dz first, and then I have divided by 2 pi. Then the other thing that's the only function of r is simply 0.1 to 0.35, 1 over r dr dz, right? I'm sorry, dr. And you know how to integrate this easily. It's nothing but we can substitute the value in here times 0.5 divided by 2 pi. That is nothing but natural log of 0.35 minus natural log of 0.1. And that's it. So, and then once you know I1, you put it in here, and this gives you the Weber, right? So that's the flux. Then what is the L12? Simply divided by I1, which is cancelled out. Therefore, L12 is simply mu 0, 0.5. Oops, let me just shift this up. Now my writing is getting worse. So L12, then you just plug in all the value that you have. So L12 is simply equal to mu 0, I1, no, I1 is gone because it's cancelled out already, right? Divided by I1. So we end up with 0.5 divided by 2 pi and natural log of this. Subtract, I can just do natural log of 0.35 divided by 0.1, right? Is that the same? Anyway, that's you plug it in, it's the same one. Let me not confuse yourself. Let me just do it the same way.